4 function calls, all frozen, all waiting, and not one useful number computed yet. That is what recursion looks like mid-flight. In this video, we write multRecur, a function that multiplies by calling itself, and then watch its call stack build up and unwind, one frame at a time. Start with the divide step. To compute 5 times 4, peel 1 5 off the front, 5 plus 5 times 3, divide again, 5 times 3 is 5 plus 5 times 2. Once more, 5 times 2 is 5 plus 5 times 1. Each line is the same multiplication, one step smaller. Stack the lines together and the whole chain appears. 5 plus 5 plus 5 plus 5 times 1, the entire answer waiting on that last small piece. Now stop. 5 times 1 is just 5, a basic fact we can solve outright. No more dividing needed. The trust is the whole strategy. Keep reducing the same problem, slightly changed, until a fundamental fact appears. Now conquer. Replace 5 times 1 with 5 and the past values back up the chain. 5 times 2 becomes 5 plus 5, which is 10. Notice that this is pure addition. The multiplication has vanished, and avoiding multiplication was the whole point. 5 times 3 becomes 5 plus 10, 15. And the original problem, 5 times 4 becomes 5 plus 15, 20. A roundabout route to an easy answer, but the pattern is what matters. At every level, we solved a very similar problem, just slightly changed, multiplying 5 by 1 less than the level above. Generalize from 5 and 4 to any A and B. The product A times B means the sum of B copies of A, written out as one long chain of additions. Extract one copy of A exactly as we extracted a 5, and what remains is the sum of B minus 1 copies of A, which is our original problem again, multiplying A by the quantity B minus 1. So the recursive step reads, the product A times B equals A plus A times B minus 1. We are using multiplication inside the definition of multiplication. Alone, that line is a trap. Nothing ever stops, and the recursion runs forever. It must be paired with a base case, a fact we know outright. When B is 1, the product A times B is simply A. 2 lines, exactly like a definition in a math class, and with them we can write code. Here is the definition as Python, def multRecur of A and B. We start with the base case because it is the simplest to think about. If B is equal to 1, the product is just A, so we immediately return A. Otherwise, we take the recursive step, return A plus multRecur of A and B minus 1. Match it to the math, the A plus part is the copy we extracted. And the star operator between A and B minus 1 is the function itself again, multRecur called on A and B minus 1. The 2 lines of math became 5 short lines of Python, and every piece has a direct counterpart. One thing should bother you. The body of multRecur calls multRecur. Using a function's own name inside its own definition is fine, but only because the argument changes. Each call passes B minus 1, so the second argument steps down. B, then B minus 1, then B minus 2, all the way to 1. Where the chain stops. Compare that with returning A plus multRecur of A and B unchanged. That version makes no progress toward the base case, so it recurses forever. Self-reference is safe exactly when every call moves closer to the base case. Watch multRecur of 5 and 4 run the way Python tutor would draw it. The main program calls multRecur of 5 and 4. That call gets its own environment, a frame, holding A equals 5 and B equals 4. B is 4, not 1, so we take the else branch and must return 5 plus multRecur of 5 and 3. That is a new function call, so Python opens a new frame for it, and the first frame goes on hold. It cannot finish. It is waiting on a result that does not exist yet. In the new frame, A is 5 and B is 3. B is not 1. So again, return 5 plus multRecur of 5 and 2. Another call, another frame, another caller left hanging. Now 3 calls are in the works, each waiting on the next. The frame with b equals 2 does the same thing and asks for 5 plus multi-recur of 5 and 1. We are 4 calls deep, and notice, no visible work has happened, no addition has been performed. Every frame is stuck at 5 plus something, kicking the can down the road. Then the last call breaks the pattern. In its frame, b is 1, the base case. No new environment. It simply returns a, which is 5. Now the values flow back up. That 5 lands in the frame with b equals 2, which was waiting to compute 5 plus 5. That is 10, and the 10 returns up 1 level. The frame with b equals 3 computes 5 plus 10, 15, and passes it up. And the original call with b equals 4 computes 5 plus 15 and returns 20 to the main program. Divide built the stack, conquer emptied it, 1 addition per frame on the way back up. Every recursive function has the same 2 halves. The recursive step calls the function itself on a smaller version of the problem. Here, a times b rewritten as a plus a times b minus 1. The base case stops the descent with a fact known outright. When b is 1, the answer is simply a. Leave either half out and the design fails. No base case means infinite recursion. No shrinking argument means no progress. Divide pushes frames onto the stack. Conquer pays them off, 1 addition and 1 return at a time, until the answer surfaces in the main program. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.